Good afternoon to all. Welcome to the 9th week tutorial session of NPTEL course Thermal Engineering Basic and Applied. My name is Ananthakrishnan. I'm a PhD scholar from Department of Mechanical Engineering, IIT Delhi. I do this problem solving session as part of my PMRF TA duty. In this week, we will see actually a few different topics that were seen from the previous cases. So we will see a cooling tower performance. What do you mean by a cooling tower? A cooling tower is actually an evaporative cooling device where the water which is used to cool the air in the case of a vapor compression systems condenser, or the heat rejected by the steam in the Rankine cycle in the condenser will be taken by the cooling water. So in order to since the cooling water takes the heat, we need to it will get heated up. Its temperature will rise, but at the same time, we do not have infinite resources of water, right? So we have to actually circulate it, and to operate it in a loop, we have to actually cool this water. So that should be done by using an evaporative cooling device. So cooling tower is one such where the water will be cooled by the ambient air, where the water temperature we can actually approach the incoming air's wet bulb temperature. So the wet bulb temperature of air is actually it's very close to it's a psychrometric psychrometric parameter where the incoming air, how much water it can take before it will get saturated at the same in an adiabatic process. So that will be given by an adiabatic saturation temperature, which is almost equivalent to the wet bulb temperature. So so the incoming air's wet bulb temperature can actually give the outgoing water's cooling temperature. So that water at that particular temperature will be used to cool the water in the cooling tower. Will be used to cool the steam in the condenser. Then the second part, we'll be seeing a few questions on IC engines. That's a new topic that we'll be discussing in this week, and different parts of SA and CA engines. These are the lectures which are uploaded in this week's course website. Then the comparison of two-stroke, four-stroke engines, comparison of SA and CA engines, compression ratio, introduction to carburetor, and regimes of engine operation. Right. So without wasting much time, we can move into the problems of this week. Choose the correct statements. Mechanical draft cooling tower size is smaller than that of a natural cooling natural draft cooling tower. Then the cooling capacity of the mechanical draft cooling tower cannot be varied. The size and power required by induced draft fan is more than forced draft. And then approach is the difference between temperature of water entering and leaving the cooling tower. Four options are there. Which out of the four are the right options? Look into it. I'll try to solve within a minute. So which out of the four is the right option? So there can be multiple answers for this particular question. Choose the correct statement. So mechanical draft cooling tower size is smaller than natural draft cooling tower size. So basically the difference between these two are cooling towers. If I try to draw the cooling tower, So in the case of we will be having hot water that is coming from the condenser water, and there will be air that will be sucked from ambient, and then the water will be cooled by evaporative cooling, where the bit of water on the surface will be taking the heat from the rest of the water to depending upon the incoming air's relative humidity will make it saturated, and thereby in this process it will get evaporatively cooled. So there are two types of cooling towers. One is mechanical draft cooling tower, and the other one is natural draft. So natural draft is the one where the air will be circulated from bottom to top based on the natural convection. It doesn't require an additional power source. Oh, yeah, but some auxiliary power source will be required, but it will be very much less. Mechanical draft is the one where a fan or a blower will be used to push or pull the air through the cooling tower. So since we are using a mechanical draft one with fan, its efficiency will be better, and the size requirement will be less compared to the natural draft. So the option one is a right option. The second one is cooling tower. Cooling capacity of a mechanical draft cooling tower cannot be varied. No, it's right. It's wrong. So the cooling capacity could be termed as how much heat will be taken out of by the water. It can be varied based on the range that we set to the it can be varied based on the range that we can set for the water. So water, depending upon the size of the cooling tower, the capacity can be varied. So if it is a small cooling tower, the cooling capacity will be less because the amount of heat rejected by the water based on the evaporative cooling will be less. And if it is more, it will be more. It will try to approach the incoming air's wet bulb temperature. The third option, the size and power required by induced draft fan is more than the forced draft. So before that, we should know what do you mean by the induced and forced draft. These two are subsections. Cooling tower will be divided as natural draft or the mechanical draft. So in the mechanical draft, there are two subsections, that is forced and induced. In the case of forced, we will keep the fan at the bottom. So if this is the cooling tower, the fan will be at the bottom. And if it is induced, the fan will be at the top. So basically, okay, then the last question is approach is the difference between the temperature of water entering and leaving the cooling tower. No. Approach is actually the temperature difference between the incoming air's wet bulb temperature and the outgoing water's temperature. The difference between the temperature of water entering and leaving, it's called range. So option 1 and 3 are the right options. So in the case of the induced option 3, then we can look into option 3. The size and power required by induced draft fan is more than the forced draft. It's wrong. Induced fan is much more energy efficient compared to that of the forced draft. So in the case of induced fan, we will be keeping it at the top. So the air will be sucked through, and it will be preventing the recirculation and ensuring better streamline flow and better cooling capacity compared to that of the forced draft. So option 3 is also wrong. Size and power required will be less compared to that of forced draft. So option 1 is the only right option in this case. Look into the second problem. It's based on the carburetor operation. Which of the following is or are correct with regards to carburetor operation? Stoichiometric air fuel ratio of the petrol is roughly 15:1, 15/1. When the throttle is suddenly opened, the mixture from the simple carburetor tends to become rich. During starting, petrol engines requires rich mixture. Rich mixture is required to dissipate excess heat at exhaust in the power regime. Yeah, the option 1 is straightforward, right? For the gasoline, for petrol, it's roughly equal to 15:1. The stoichiometric air fuel ratio is the ratio of the mass of air to the mass of the fuel at which it will ensure complete pure combustion, producing carbon dioxide and water. In certain cases, lean mixture, that means that the air quantity will be much higher compared to that of the stoichiometric air fuel ratio. In that case, there can be possibility of the formation of much more NO2 nitrous oxides. But in the case of rich mixtures, where the air to fuel ratio will be lesser than that of the stoichiometric air fuel ratio, there can be a possibility of incomplete combustion, resulting in a mixture of carbon dioxide, carbon monoxide, and water. So option 1 is right. Option 2, when the throttle is suddenly opened, the mixture from the simple carburetor tends to become rich. No, so when it is suddenly opened, what happens is that the when the throttle is a choke point. When it is opened suddenly, instead of this one, if it is open like this, the airflow will not be choked in this case. So the velocity will decrease compared to the previous case. When the velocity decreases, pressure increases, and the pressure gradient delta P for the fuel will decrease. This will result in lesser fuel that will be injected into the airstream. Airstream resulting in a lean mixture. So where the air to fuel ratio will be greater than 15:1 stoichiometric ratio. So this is wrong. This is lean. Then the third one, during starting, petrol engines require rich mixture. Yes. So in the case of cold start cases, when the incoming air's temperature will be very less, the combustion will be really poor. So in order to accelerate it, in order to improve the combustion efficiency, initially for a few bit time, initially for a few seconds, we have to turn on the choke. And in that case, choking means we are reducing the airflow. So once we reduce the airflow, we are restricting the airflow passage. So the velocity increases, pressure here decreases, and once the pressure here decreases, the pressure gradient from the fuel to the air side will increase, adding more fuel to the mixture and making the air fuel mixture rich. So this rich mixture can improve the combustion at the initial phase, providing the much required increase in the temperature uh, in the cylinder. So this is right. 1 and 3 are right. Then fourth option, rich mixture is required to dissipate excess heat at exhaust in the power regime. Yes, this is right. So in the power regime, there will be four. Take the case of a four-stroke engine. There will be suction. There will be compression. Then there will be power cycle, followed by the exhaust. So rich mixture is required to dissipate excess heat uh, at exhaust in the power regime. Yeah. So uh, if the mixture is rich enough, a bit of the portion of the heat will be delivered to the uh, fuel itself, and it will be used for dissipating the excess heat. So option 1, 3, and 4 are right. Look into the third problem. Choose the most appropriate option in relation to the statements below. In automotive petrol engines during idling operations, a rich mixture is required. Yeah. And then option statement 2 is a rich mixture is required to prevent damage or degradation of the exhaust manifold. Yes. So we have seen the fourth option of the previous problem. We need to provide a rich mixture to dissipate the excess heat. So option 2 is right. Then option 2 is right. In the case of first, in automotive petrol engines during idle operations, a rich mixture is required. Yeah, during idle, during starting, cold start cases, we need to provide a rich mixture to provide the sufficient increase in temperature. So option 1 and 2 are right, but is option 2 the right explanation for option 1 or vice versa? No. Both statement 1 and 2 are right, but they are not the correct explanation of statement 2 is not the correct explanation. So option 2 is the right answer. Now we can see a question based on the condenser. It's based on a surface condenser, which operates with a steam turbine. The vacuum near the inlet of the air pump is 69 centimeters of mercury when the barometer reading is 76 centimeter of mercury. The temperature at the inlet of the vacuum pump is 30 degrees Celsius. Air leakage occurs at the rate of 60 kilogram per hour. Determine the cooling and the capacity of the air pump in meter cube per hour and the mass of vapor extracted in air in kilogram per hour. The second option, the second part of the question, the dimension of the reciprocating air pump cylinder if it runs at 240 RPM and the L by D ratio is 1.5. Look into it. I'll also try to solve within a minute. So we can look into the problem. It's a surface condenser operating with a steam turbine. So steam turbine. So the steam that it is expanded in the turbine will be condensed by rejecting heat to the external water source in a condenser. So the vacuum near the inlet of an air pump is 69 centimeter of mercury when the barometer reading is 76 centimeter of mercury. The temperature at the inlet of the vacuum pump is 30 degrees Celsius. Air leakage occurs at the rate of 60 kg per hour. Determine the capacity of the air pump in meter cube per hour and the mass of vapor extracted with air in kg per hour. So we have to actually determine the absolute air pressure at inlet to the air pump. So in this case, the absolute pressure to the inlet of the air pump the vacuum near the inlet of an air pump is 69 centimeter of Hg and the barometer reading is 76 centimeter of Hg. So the difference between the vacuum and the barometer reading will be the absolute pressure at inlet to the air pump. So 69 centimeter is the vacuum and 76 is the barometer reading. So 76 minus 69 into 10 power 7 centimeter. So in order to get the absolute pressure, we have to actually use rho g into s, rho of the mercury into g 9.81 into the h, that is this term. So it's 76 minus 69. So that will be 76 minus into 0.013591 into 10 power 4 into 9.81. So this will be giving us the absolute pressure at the inlet to the air pump. So then we have to actually determine the partial pressure of vapor at 30 degrees Celsius. So basically this is saturated condition. So we can take it as saturation pressure at 30 degree. So that will be equal to 4.246 kilopascal. Therefore, partial pressure of air will be equal to PA equal to PT minus PS is equal to 5.09 kilopascal. So this is a vacuum pump. The vacuum near the inlet of the air pump is 69 when the barometer reading is 76. So the difference between these two will be giving us the absolute pressure. So 7 centimeters will be the difference, and at the inlet to the vacuum pump, and using the density of the mercury and the G value, we can get the absolute pressure. That minus saturated pressure will be giving us the partial pressure of vapor at 30 degrees Celsius. Therefore, the partial pressure of air will be equal to Pt minus Ps is equal to 5.09 kilopascal. Now we have got the partial pressure of air as well. Then it's mentioned that the air leakage occurs at the rate of 60 kilogram per minute. So the volume of 60 kg air at the pressure of 89.112 kilopascal will be equal to. So the incoming actual pressure will be based on 76 centimeters of mercury, and then the vacuum will be equal to 69 centimeters of He. So based on that, we can get the volume will be equal to MRT divided by pressure. So M will be equal to 60, R will be 0.287 kilojoule per kilogram, and the temperature will be 303 Kelvin divided by 5.09. That is the pressure in terms of kilopascal. So this will be kilojoule and this will be kilopascal. So gets cancelled each other. So it will be equal to 1025.1 meter cube per hour. So using the air side, we can actually get the volume. This volume will be equal to the capacity. Volume flow rate will be equal to the capacity of air pump in terms of meter cube per hour. So now we have to determine the mass of the vapor extracted. So the mass of the water vapor going with air will be equal to the volume flow rate divided by so this is actually the meter cube per hour. In terms of kg per hour, you have to get, so you have to divide it by the specific volume. Specific volume of the gas at 30 degrees Celsius. From the steam table, we can get it as 32.89. So we'll be getting it as 31.17 kilojoule per hour. So that is a mass of water vapor going with the with air. So these two are the first two parts, and then we have to determine the dimension of the reciprocating air pump if it runs at 240 RPM and the L by T ratio is 1.5. You know the volume flow rate, that will be equal to 1025.1. That will be equal to pi by 4 into D squared into L into pi by 4 into, this is in terms of meter cube per hour. So this will be meter cube per cycle. Then per RPM, then we have to multiply it by the RPM. So that will be equal to 240 RPM is given in the problem. So that will be revolution per minute, 240 multiplied by 60 for revolution per hour. So this will be equal to 240 into 60. It will be pi by 4. The L by D ratio is 1.5, so we can write L as 1.5 D. So it will be 1.5 D cube into 240 into 60. So in this we'll get D is equal to 39.24 centimeters, and the corresponding L is equal to 1.5 times of this one. That will be equal to 58.86 centimeters. So it's a slightly tricky question because this is nothing like what we have seen in the previous cases. It requires a bit of psychrometric calculation. So in this case, 76 centimeters is the total barometer pressure, and 69 is the vacuum pressure. So the difference in the pressure that will be taken at the inlet, that will be the actual pressure at the inlet. So that will be equal to that will be the pressure that will be leaked into uh, that will be actually leaked into the vacuum pump. So using that, we can get the partial pressure of the vapor at 30 degrees Celsius from the psychrometric table, and the difference will give the partial pressure of the air. Using this partial pressure of the air and the mass of the air and R and T, we can get the volume flow rate. So this will be the volume flow rate of the condenser, and then in a volume flow rate, the capacity of the air pump, and using this uh, the volume flow rate and dividing it by the specific volume of the gas at 30 degrees Celsius, we can get the mass of the water vapor going with the air, that is 31.2. Then equating this volume flow rate with the dimensions as in the volume and the revolution per hour of the vacuum pump, we can get the dimensions as well. That will be facilitating this much volume flow rate. Look into the first problem. It's also a multiple choice question. During the intake stroke, when the piston moves from top dead center to the bottom dead center, the pressure inside of the cylinder will be equal to the atmospheric pressure, greater than the atmospheric pressure, less than the atmospheric pressure. Look into it. I'll also try to solve. So the question is, during the intake stroke, when the piston moves from the top dead center to the bottom dead center, the pressure inside the cylinder will be. So if this is the piston and this is the top dead center and this is the bottom dead center, when it moves from the top dead center to the bottom dead center, the pressure inside the cylinder, it's actually not compressing, it's expanding. So in that case, the pressure inside it is actually trying to fill in air from the outside, the air fuel mixture from the outside. So it should be less than the atmospheric pressure during the suction intake stroke. So the pressure, once it starts filling in air, it reaches the atmospheric pressure at some stage where nearby the atmosphere pressure in some stage. So the answer is 3. The stoichiometric air fuel ratio for SA engine is 15:1. What is the air fuel ratio for high economy? 16:1, 15:1, 12:1. So for that, we need to actually look into the curve that shows the fuel efficiency, the power production with respect to the air fuel ratio. So this is 15:1. That is the stoichiometric one. This will be say 20 and this will be 0. So the stoichiometric air fuel ratio is the one where we'll be getting the the complete combustion. So as we move from left to right, it will be lean mixture where the air content will be more, and if it goes to right to left, it will be rich mixture where the fuel content will be more compared to the stoichiometric case. So we'll be getting the maximum power in the case of SA engine at somewhere around 12.6 is to 1. So this is just the complete combustion, the stoichiometric. The maximum power is something that something that we obtained towards a slightly more richer side. But the best fuel economy is the one where we'll be getting for correspondingly for a lower fuel in flow rate, we'll be getting a better the maximum fuel efficiency. So if you use a slightly less flow rate of the fuel, it will be ensuring complete combustion and we'll be making sure that the entire quantity of the fuel will be used. This is based on the experimental analysis. So in that case, if you provide slightly more this one air, it will ensure complete combustion and we'll be making sure that we'll be getting better mileage in the common parlor. So best fuel economy is somewhere here, is in the lean range. So the answer should be 16:1. Maximum power 12:1, 15:1 is the stoichiometric air fuel ratio. Look into this problem. This is also a multiple choice question. How does the flow of air occur in the natural draft cooling tower? Due to the given air vents and vacuum ports, natural pressure head density between the cold outside air and the humid inside air, variation in pressure of both cold outside and the humid inside air, because of difference in the volume between cold outside air and humid inside air. So we have seen in the previous one of the previous question, natural draft cooling tower works on natural convection. So it works on difference in density. So we can ignore every other version. It's a density difference between the cold outside air. It is a density difference between the cold outside air and the humid inside air that matters. Cold outside air will be at a lower density, will be at a higher density. Once it starts taking moisture, its density decreases and it starts flowing upwards. And then it will start exchanging heat with the water and cools the water in the process. So option 2 is the right one. Look into the 8th problem. It's a numerical. Uh, a surface condenser receives 250 ton of hour of steam at 40 degrees Celsius with 12% moisture. The cooling water enters at 32 degrees Celsius and leaves at 38 degrees Celsius. The pressure inside the condenser is found to be 0.078 bar. The velocity of circulating water is 1.8 meter per second. The condenser tubes are of 25.4 millimeter outer diameter and 1.25 thickness. Taking the overall heat transfer coefficient at 2600 watt per meter squared Kelvin, determine A, the rate of flow of cooling water, the rate of air leakage into the condenser shell, the length of tubes, and the number of tubes. How will you try to solve this problem? So we have been given the the mass flow rate of the steam and the temperatures with the moisture. the cooling water enters at 32 degrees Celsius and leaves at 38. So this is a surface condenser where the steam will be present inside the shell region, and the cooling water will be present inside the tube. The pressure inside the condenser is found to be 0.078 bar. So this is the condensing pressure. So the velocity of the circulating water is 1.8. The condenser tube's dimensions are given. Overall heat transfer coefficient on the is also given. U value is given. We have to find the geometry and the rate of the flow of cooling water, the length of the tubes, number of tubes, and the rate of air leakage into the condenser shell. So we have seen a problem previously regarding the air leakage uh, in the vacuum pump at the inlet of the vacuum pump. So the difference between the vacuum pressure and the corresponding pressure at the side will be giving the air pressure. So here it is straight away given as 0.078 bar. So if you try to draw, so this is a shell side and this is the tube side. So this will be the cooling water that will be inside the tubes, and then the steam will be in the shell side. So the steam, it's a condensing steam at a constant temperature 40 degrees Celsius, and the cooling water temperature increases from 32 degrees Celsius to 38 degrees Celsius. So final delta T at this particular point will be equal to 2 degrees Celsius. The initial delta T will be equal to 8 degrees Celsius. This is the length. In this particular problem, we have been given the moisture content of the steam at the inlet, that is 12%. Uh, the dryness fraction, corresponding dryness fraction will be equal to 0.88. So if you try to observe this in a TS diagram, so it will be consider an isentropic process in the steam turbine. It will reach somewhere here within the Weber dome. So this is the condensation process 2 to 3. So in this case, x2 will be equal to 1 minus 0.12. That will be 0.88, the dryness fraction at the inlet. H2 will be equal to HF plus X into HFC. So the temperature inside the condenser, the pressure is given as the steam temperature is given as 40 degrees Celsius, right? So within the condenser, so we have to find the HF and HFC from the steam table corresponding to 40 degrees Celsius. We'll be getting it as so we make some difference. So HF will be equal to H3. It's a saturated liquid enthalpy. So this is just a mathematical manipulation. H2 minus H3 will be equal to HFG uh, at 40 degrees Celsius. This will be equal to 2118.16 kilojoule per kilogram. So this is done. Now we have to find the first part, the rate of the flow of cooling water. For that, we have to look into the energy balance within the condenser. So the energy balance uh, in the condenser will be given as the mass flow rate of the steam into H2 minus H3. That will be equal to the mass flow rate of the cooling water into CPC into TC2 minus TC1. So this is the cooling water temperature TC2 and this is the TC1. The difference will be equal to 38 minus 32 will be equal to 6. Therefore, the mass flow rate of the steam is, we can find the mass flow rate of the cooling water. So steam is given as 250 ton per hour. And then the difference is 2118.6 kilojoule per kilogram. Then MC is a cooling water, and you can take it to be Cp equal to 4.18 specific heat of water. It's incompressible, so it's not going to change. And then Tc2 minus this one will be equal to 38 minus 32. Therefore, the cooling water, the mass flow rate of cooling water will be equal to MC equal to, solving this, it will be 5855.2 kilogram per second. Now we have to determine the second part, rate of air leakage into the condenser shell. So this is slightly tricky. We have to actually use, just like the previous case, we have to use the ideal gas equation for the air side. In that case, in one of the previous question, the vacuum pressure as well as the barometer pressure were given, and we use the difference to get the vapor pressure of the air. So basically, we have to actually determine the air leakage into the condenser shell. So in this case, using the ideal gas equation, the PV of air will be equal to mass flow rate m air into R into T of air. So in the condenser, temperature will be equal to 40 degrees Celsius, 40 degrees Celsius. So that will be equal to 313 Kelvin. And the saturation pressure is given as 0.07375 bar at the steam temperature of 40 degrees Celsius. So the basically the total pressure is given as 0.078 bar, and the saturation pressure of the steam at 40 degrees Celsius is 0.073 bar. Therefore, the remaining pressure will be the pressure of air in the condenser. So that will be equal to 0.078 minus 0.073. That will be equal to 0.00425 bar. So now we got the pressure of the pressure on the air side. We can denote it by equation 1. Then we have to determine basically what we have to determine is the mass flow rate of the air. Then we have to determine the volume flow rate of the air. That will be the total volume. Volume of the condenser shell side will be same as that of the volume of the steam. Will be same as that of the volume of air. Therefore, V air will be same as that of V steam. That will be given by mass flow rate of the steam divided by density, or the specific volume multiplied by the specific volume. So mass flow rate of the steam will be 250 ton per hour into steam Vs will be written as Vf plus X Vfg at 40 degrees Celsius, and this will be getting it as 17.2 meter cube per kg. Therefore, the mass flow rate of the steam, therefore the volume flow rate of beg your pardon, there's a small correction. Yeah. For the mass flow rate of the air from equation 1, before that we can denote them by this by equation 2 and this by 0.3. Therefore, equation 1 becomes P will be equal to 0.00425 bar multiplied by 10 power 5 into 250 into 10 cube divided by 3600 mass flow rate into 17.2 meter cube per hour kg. That will be equal to the mass flow rate of the air into 287 into temperature 313. So this will be giving us a mass flow rate of the air that will be equal to 5.651 kg per second. It's based on the ideal gas equation. And the last part, we have to determine the length of the tubes and the number of the tubes. So we attempt the last part of the question where we'll find the number of tubes and then we back calculate to get the length of the tubes. So how can we get this? So we have to use the Q equation. So Q will be equal to mass flow of the heat transfer that takes in the condenser. That will be equal to mass flow rate of the condenser into Cp of the condenser into delta T. That will be equal to UA LMTD. That is the overall conductance into outside area into that will be same as that was the mass flow of the steam into H2 minus H3. What we have determined from this one is the area, and from the area we can get the total number of the tubes and the length of the tubes as well. So in this one, the condenser tubes dimensions are given. So we know the area of a single tube, but we will not be knowing the length of the tube. So we have to actually determine. We have to determine the actual outer surface area, and from that we can get the length. So U is given, so we can calculate area if you know the LMTD. So LMTD could be written as delta T1 delta T1 minus delta T2 divided by ln of delta T1 divided by delta T2. So it's it's kind of an average. So logarithmic mean. It takes into account the logarithmic mean because the temperature difference profile will be following a logarithmic curve. So it will be 8 minus 2 divided by ln logarithm natural log of natural log natural log of natural log of natural log of delta T. So it could be taken as the natural log of the temperature difference on one side as well as the other side. On one side it is 8 and the other side is 2. So the LMTD will be equal to 4.33. So from this one we can calculate the UA value. The total heat transfer we can obtain from the other equation which correlates the cooling water temperature change as well as the mass flow rate, or we can use the other side, the condensing steam and the enthalpy change. Then we can get UA into LMTD 4.33, take the steam side. We know 2500 ton per hour is the flow rate of the steam. We multiply it by the enthalpy change encountered by the steam in the condenser when it exchanges heat with the cooling water from point 2 to 3. That is basically the enthalpy of vaporization at 40 degrees Celsius. And from this one, you can get the UA. We know the value of U that's given in the problem, that is overall heat transfer coefficient is given as 2600 watt per meter squared Kelvin. So this one will be, and then we can get the outer area. Therefore, the outer area will be equal to, solving this, we'll get it as 13,066 meters squared. But this doesn't tell the whole story. This is just the outer area, the total outer area. But we know the dimensions of a single tube. We have to somehow find the number of tubes that we require to facilitate the energy transfer. For that, we know one thing, the cooling mass flow rate. We have seen in the previous, the first part of the problem, the cooling water mass flow rate is 5855.2. But this takes into account the flow rate of the steam in all the tubes. So as we have seen, the flow rate of the cooling water occurs through the tube side. The shell side is where the steam condenses. That will be 5855.2 kilogram per second. That will be equal to number of tubes multiplied by the cross-section of the cross-section area of the tube into the density into the volume flow rate. Therefore, the number of tubes. This is one of the crucial parameters to determine the actual length of an individual tube. So the number of tubes will be just divided. We'll get it as 7898. From this one, we can get the we know the overall area, right? So then from based on that, we can get the length of individual tube. That would be equal to the number a single tube's cross surface area for heat exchange. That will be equal to pi d0 into L multiplied by the number of tubes. Therefore, the length of tubes L will be equal to A0 divided by n pi d0. That would be equal to 20.73 meters. So that completes this problem. It was a slightly tricky problem because we have to determine the rate of flow of cooling water and the rate of air leakage into the condenser shell and the length of the tubes and the number of tubes. It was option B, the part B of the problem that was slightly tricky, where we have to find the air leakage into the condenser shell. This is slightly a different variant from the question that we have seen initially. Here we have to determine the air leakage into the condenser shell. So we have actually used the ideal gas properties of the air. In order to find the mass flow rate of the air, we need to know the pressure. The pressure will be same as that of the condenser side pressure. It's already given the problem. The volume flow rate of the air, on the condenser side, air will be mixing with the steam. So in that case, the total volume occupied by the steam will be same as that of the air volume. So we can use that particular property to get the air volume, and then the temperature will be same as the steam condensing temperature, and R will be the gas constant of air, 287. So from that we can get the mass flow rate of the air. Once the mass flow rate is known, that's a straightforward one. Then the energy balance within the condenser will give the flow rate of the cooling water. The length of the tubes and the number of tubes needs a bit more ingenious calculation, where we have to take the energy transfer from the shell side to the from shell side to the tube side. And in that case, we can use an overall heat transfer coefficient based equation, UA LMTD based equation. That's a third equation that correlates the heat transfer. And using that and an overall heat transfer coefficient from the steam side to the cooling water side, we can get the overall area required. Based on the overall area and the area of an individual surface area of the individual tube, we can get the number of tubes and the corresponding length of the tube as well. And one more equation is required to get the length of the tube, that is the total mass flow rate of the cooling water. We have already obtained that from the first part of the problem and used the number of tubes and the cross-sectional area, just like the continuity equation, we get the number of tubes. That's all this problem. We can move into the next one. This is a problem based on the IC engine carburetor. A carburetor is required to supply air at 5 kg per minute and fuel at 0.5 kg per minute. The fuel specific gravity is mentioned plus 0.75. The air is initially at 1 bar and 300 Kelvin. Calculate the throw diameter at the choke floor for a flow velocity of 100 meter per second. The velocity coefficient is given as 0.8. Try to solve. I'll also try to solve within a minute. Yeah, have you tried to solve this problem? It's on carburetor. So we need to deliver air at 5 kg per minute and fuel at 0.5 kg per minute. The fuel specific gravity is 0.75. Air is initially at 1 bar and 300 Kelvin. And we have to calculate the throat diameter of the choke for a flow velocity. It's very straightforward. We have to actually find the velocity, the velocity of the fuel at the throat. We know the velocity coefficient of 0.8. So that means that initially it is given a flow velocity of 100 meter per second is given. And the velocity coefficient of 0.8 is also given. The throat area is the area of the lowest cross-sectional area. So in that particular area, the pressure will be the lowest. Once the velocity is highest, just use the Bernoulli's theorem. So once the velocity is highest at that particular point, pressure will be lowest, and the pressure gradient from the fuel tank towards the throat area will be high. And this will make sure that more fuel will be passing, will be injected to the airstream. And we can try to tackle the problem in such a way. We have already seen in the lectures regarding the throat velocity calculation, how we can get it from the ideal gas equations, as well as the Bernoulli's equation. So we take two cross-sectional areas, one at the inlet as well as the throat area, and we equate the kinetic energies as well as the pressure energies. And this is air that flows from the point A to point B. Since I haven't drawn the figure, it will be quite confusing for you. I'll draw a figure and we'll make sure and we'll try to elaborate it in a better manner. So consider the carburetor, the air channel. This is the incoming air cross section, and there is a throat area or a point of smallest cross section. We can denote it by point B, and this is the point from where the fuel will be injected based on the pressure difference. This is the fuel tank. This is the fuel. This is the fuel inlet port that comes from the actual fuel tank, and it will be having a pressure. The air channel here will be exerting a pressure on top of the fuel, and this will be an air vent. This will make sure that it is the ambient pressure that acts here as well. So basically, it is a high difference that dictates the pressure of the pressure of point B. So that is done. Now we try to tackle it in the normal way, which I have mentioned in the previous case. So here we know the velocity coefficient that is given as 0.8. What is velocity coefficient? It's the ratio of the velocity at the inlet to the throat point. Or vice versa. So basically, the throat point velocity will be higher compared to the inlet velocity. That's what I meant. So it could be written as VA by VB. The we know the cross-sectional area, the point with the smallest cross-sectional area will be having the highest velocity, because the air flows in a continuous stream. It doesn't have any leakage as well. So applying the continuity between A and B, continuity equation between A and B, will be getting a high velocity at point B. So we know velocity at point B will be equal to VA divided by 0.8. In this particular problem, we can denote point B's velocity as 125. It's given the flow velocity of 100 meter per second, not at the throat point. So straight away you can calculate 100 divided by 0.8, it's 125 meter per second. So that part is clear, right? Now we can move into the actual energy balance steady flow energy equation between the point A and B. So we have this the enthalpy change happening between A and B, and the velocity change. For the time being, neglect the gravitational head that will be taken into account. That will be very minimal. Consider it to be a horizontal channel through which air is passed through. So for that, both the points of A and B will be having the same head. So the enthalpy change will be reflected in the change in velocity. So we can denote that the point B's velocity could be represented in terms of the pressure difference between point the point A and B, as well as the temperature difference, basically ideal gas equation. So we need the enthalpy, right? So it's air. If it was a fluid, say another fluid, say water, we could have directly taken Cp into T for the energy part. For the enthalpy part, we could have taken the this one, Cp into T. But in the case of air, we can actually have a bit more complications. We need to take into account the internal energy change plus the PV component. So these two will be taken into account. So we already have another set of equations that will be coupling the enthalpies, right? So we can take into account the pressure of the point B and point A. So that equation which we have seen in the lectures is basically equating the kinetic energy and the enthalpy change. So that will be equal to 2Cp into TA multiplied by 1 minus of pressure difference between point B and point A. This raised to gamma minus 1 divided by gamma. So what we can consider between point A and point B is that it is not actually exchanging heat with the surroundings. We can consider this to be an adiabatic case. So point A and point B, the state points of the pressure and the volume actually follow ideal gas and adiabatic equation. So we for the time being neglecting whether this is isentropic or non-isentropic. We can use a reversible adiabatic equation. In this case, the PV ratio gamma is a constant. So equating these 2 points, we can get the enthalpy change in the form of this equation, and we can get the kinetic energy of the point B, the velocity of the point B using this equation. We know the velocity is 125 square. Just take this root out, and then the Cp of air, that is 1.05 into 1.005 into 10 cube, and the temperature is 300 Kelvin. So straight away we know the incoming it's mentioned the pressure at the inlet will be equal to 1 bar, and so for the time being we just leave it there itself. So the pressure at the point B is something that we do not know, and then the gamma will be 1.4 for air. We substitute that, and the only unknown in this problem is the pressure at the point B, so we'll get it as 0.91 bar. So it's less than the pressure at the point A, that is the incoming air. It's straightforward because it's a throat area, velocity will be more, pressure will be less. Bernoulli's equation, or from the steady flow energy equation, we can actually derive it. We have actually determined it from the steady flow energy equation. And now it is known, we can calculate the flow rate of the specific volume of the air. That will be RT divided by P, that will be equal to 0.861 meter cube per kg. So once that is done, we have to actually determine the throat area, right? How will we get the throat area? In order to get the diameter at the choke throat point, we have to use the continuity equation. There is no other way. Uh, how are we going to use that? That is the point that we need to address. The mass flow rate from continuity equation would be written as A into B divided by nu. Instead of rho A B, since it's air, we can actually use a specific volume of air at the point B. From this one, we can get area at the point B will be equal to the mass flow rate of air at point B into specific volume at point B divided by velocity at the point B. The reason we have done all the gymnastic at the beginning is to determine the state point B. We know the pressure, we have determined the specific volume straight away. How can we get the specific volume at point B? We know the pressure. We know the pressure at both the points. We know the specific volume at the starting point. We have just calculated right now VA. Using as I mentioned, the adiabatic equations between point 1 and 2 is the adiabatic state equation P raised to gamma is a constant. So just that P into specific volume raised to gamma equal to PE VB specific volume of raised to gamma constant. Therefore, from that, nu B will be equal to PA divided by PP raised to into VA raised to gamma the whole power 1 by gamma. Therefore, nu B will be equal to 0.919 meter cube per kg. That's given. Almost every issue in the problem is solved, and we can just finally determine the cross-sectional area. We know the mass flow rate that will be same 5 kg per minute, 5 by 60 into nu b 0.919 divided by vb, the velocity at the point 2, that is 125. It's a throat point. So this will be equal to the area AB. Therefore, this will be equal to pi by 4 into the throat point's diameter, pi by 4 into dB squared is equal to this much value, 5 by 60 into 0.919 divided by 125. Therefore, the diameter of the choke or the throat point dB will be equal to 0.027 meter, that is 2.7 centimeters. So if we try to observe, unless otherwise we knew the velocity coefficient, we couldn't have solved this problem. So this is the additional information that is required in the problem to create a connection between the first point and the second point. Once you obtain the velocity coefficient, once we already knew the velocity at the inlet, we determine the velocity at the throat point. That is given. Velocity at the throat point is given. The ultimate aim of this problem is to determine the throat diameter of the choke. For that, we require the continuity equation or the mass flow rate. So using the mass flow rate, we need to know mass flow rate will be equal to area into velocity divided by specific volume. The velocity coefficient will give the velocity at the throat point. So that is done. The diameter is something that we have to determine. Mass flow rate is given. Then the other property that we need to determine is the specific volume at the point B. The specific volume at the point B, it's an ideal gas kind of thing. Case for the time being, we are ignoring the fuel content in the air. We are just considering the air at the starting point A and B. So we can determine the specific volume at the point B. How? We need to determine the pressure at the point B, and using the adiabatic equation between A and B, we can get it. How to get the pressure at our state point B? Using the velocity, this equation. Vp is equal to root of that is steady for energy equation between the point A and B. With a small twist to the pressure at the point B and A. We actually normally in the case of nozzles, we write the velocity at the exit will be equal to the change in enthalpy, the root of 2000 into change in enthalpy, right? So just similar to that, we get it in the form of the pressures. Using that, we'll get the pressure at the state point B and get the specific volume, calculate the diameter of the movement. So it's a straightforward problem, but it requires a bit of overall understanding of the concepts. Look into the last problem of the session. It's a straightforward, another straightforward problem. Just need to apply the formulas, and not like the previous case. This is straightforward, really straightforward. The cubic capacity of a four-stroke spark ignition engine is 245 cc. The diameter to length ratio is 1.1. The clearance volume is 27.22. We have to calculate the bore or the diameter and the stroke length and the compression ratio of the engine. So what does this problem tell? We know the stroke volume. What is the formula of stroke volume? It is equal to pi by 4 into the diameter squared. That is cross-sectional area multiplied by the length or the stroke length. So the stroke length is given as the diameter to the stroke length ratio is 1.1. So the stroke length will be equal to diameter divided by 1.1. So we can denote everything in terms of the diameter and we can calculate. And this value is given as 245 cc. And from them we can get the diameter or the bore will be equal to 7 centimeters straight away quote. And the stroke length LS will be equal to D into 1.1, that is equal to 7.7. That's beg your pardon, D by 1.1. D by 1.1, that is 6.36. 6.36 centimeters. So that is done. So the first two portions of the problem we have completed. Now the last portion we need to determine the compression ratio of the engine. So what do you mean by compression ratio? So if you try to observe an IC engine, note the entire length will be equal to the stroke volume. Not the entire volume will be equal to the stroke volume. There will be a bit of volume that will be unused, where the fuel will be actually the fuel air mixture will be actually compressed. So this is the piston. This is the connecting rod, and this is the crank. So basically, once the crank rotates, this rotation motion of the crank will be converted to the reciprocating motion of the connecting rod. So it will be try to push inside, and in this process, initially there will be there will be a suction, and then when it moves inside, it will be compression. It will be compressing the air fuel mixture, and then it will be it's a spark ignition, right? It will be providing a spark, and then that will be providing that will be initiating the combustion, and based on that combustion there will be a power stroke, and it will be actually the stroke in which the power will be delivered to the crank, and it will be rotating the it will be actually providing the power for motion of the engine, and then there will be an exhaust cycle. So exhaust stroke. So there are actually 4 stroke, and these 4 strokes combine together to make it a 4-stroke engine. And we are actually not going into the details of all that. Just want to give you an overall picture of what a 4-stroke engine will be having. The details of a 4-stroke engine. So this is a top dead center and this is a bottom dead center. There will be a small volume which will be in which the volume, the total air fuel mixture will be compressed. So that will be equal to the clearance volume. So the compression ratio could be written as it's basically a mathematical term equal to the total volume divided by the clearance volume. For that, we require, this will be the total volume and this will be the clearance volume. The total volume will be equal to the stroke volume from the top dead center to the bottom dead center plus the clearance volume divided by the clearance volume. Could be written as Vs plus Vc divided by 1. We know the total stroke volume, that the cubic capacity of the four-stroke engine will be given as 245. This is actually the stroke volume. It doesn't actually deal with the total volume. So 245, we already know. We have calculated the clearance volume. How? We didn't calculate it, right? We have to calculate. So the clearance volume will be equal to, do we need to calculate it? No, it's already given in the problem 27.2. So that makes our life easier. So 245 divided by 27.2 plus 1, it's straightforward. The compression ratio is 10. So basically we need to calculate how much will be the compression ratio based on the volumes that are available in the problem. One is a stroke volume and the other one is a clearance volume. The total volume divided by the clearance volume will be the compression ratio. That will be same as that of the stroke volume divided by compression, the clearance volume plus 1. And we will be getting it as 10. That completes a set of problems that I had for this week. In this week, we have actually got a brief understanding of what cooling towers, what cooling tower is, the different types of cooling tower, natural draft as well as mechanical draft, and the different subsections of the mechanical draft ones, the forced and induced ones. And then we have seen a few problems on the surface condensers, and this problem was kind of similar to the problem that we had taken in the later part of the session, but here it involved a vacuum pump, and we have to determine the pressure of the air based on the difference in pressure. And once that is done, now we have to determine the diameter and the length of the reciprocating air pump based on the capacity. And then we had moved into the carburetors and spark ignition engines, and we have seen a few numerical and multiple choice questions based on the MOSFET. That's it for this session. In the next week, we will actually move. We'll actually delve quite deep into the internal combustion engines. We'll see the simple flow type carburetors, the mass flow rate of the fueling, and the limitations of the simple carburetors, and then the engine operating mean effective pressures, and the indicator diagram, performance analysis parameters of the IC engines, alternative fuels used in the IC engines. So if you will see a few numericals based on that, a few numericals and multiple choice questions based on that in the next week session. Before that, if you have any issues, if you have any queries, you can actually post it in the course forum available in the website. And that's all. Thank you.